Here are the answers to some short and sweet multiple choice questions on hybrid orbitals. Question 1, the change in hybridization that happens when methane combusts. You could write the balanced equation, maybe you don't need it. In a combustion, we've got the CH4 methane, and we know that the carbon on the product side would be in the form of carbon dioxide. If it helps, you can draw the structures, but maybe by now we kind of know that CH4 is a tetrahedron. There are 4 electron groups around the carbon, so I need 4 equal energy bonding regions. That's sp3 hybrid orbitals, and carbon dioxide is linear. There are 2 electron regions around the central atom that repel 180 degrees. That would be the sp hybrids. Number 2, and the rest of them have this massive carbon structure. We want to know the bond angle around carbon 1. So around carbon 1, I see that there are 1, 2, 3, 4 electron groups. On paper, it kind of looks like a flat cross. It kind of looks like 90-degree angles, but please don't pick 90. That tetrahedral shape is not really a flat cross. We can put those atoms farther than 90 degrees if we go in 3 dimensions. So here's really the structure of that carbon atom. There would be the 3 hydrogens, but they would not be flat. They're 109.5 degrees. Question 3, what hybrid orbitals are used to create the bonds around carbon 5? Around carbon 5, I see 3 groups of electrons that repel as far apart as possible. The farthest I can get those 3 groups would be a trigonal planar, 120-degree angle, and that would be sp2 hybrids. Question 4, what hybrid orbitals are used to describe the bonding around oxygen B? Around oxygen B, we've got 2 bonding electron groups and 2 lone pairs. So there are a total of 4 electron groups on the center. Anytime there are 4 electron groups on the central atom, I got a picture that 3-dimensional tetrahedral rocket ship. Well, in this case, 2 of those groups just aren't really bonding groups. They're lone pairs. But I'm still going to be left with that bent shape. There's no way that I could pop 2 atoms off a tetrahedron and be left with anything linear. And so it would kind of maybe look like this, where it would be bent. And they're trying to show it with proper angles in this model that, yeah, it's not linear, it's bent. It's the bent with 4 total electron groups. So anytime I need 4 electron groups around the center, whether it's the true tetrahedron, it could be the trigonal pyramid, or it could be this bent with 2 lone pairs, I'm going to need those sp3 hybrids. Angles of approximately 109.5 degrees, but in this case a little bit less because those lone pairs take up a little more space than a bonding pair. And finally, question 5. True or false? The atoms around carbon 1 lie in one plane, which just means, is it flat? And of course we've got this giant molecule and we're typing it on paper, so we have to type it flat. But in reality, we said carbon 1 would have 109.5 degree angles. It's a tetrahedron, and tetrahedrons are not flat. So lying in one plane means, is it gonna be flat? No, not around carbon 1. What about carbon 5? Well, now we'd say yes. Now carbon 5 was that trigonal planar, 120 degree flat triangle. Yes, carbon 5 would be flat, but carbon 1 would not.